Okay, in this video we're going to work through, this is actually the very last lesson in this guided notes book, so you're going to have to turn all the way to the back. It's about the third to last page. We've covered quadratic functions quite a bit, so now we're just going to kind of connect it to all the functions that you've seen thus far. So your goal today is that you'll be able to distinguish between linear, exponential, and quadratic data models. So data models would be things like a table. Can you tell what kind of function it is if we put some data in a table, on a graph, or in the equation? Now the graph ones maybe are the easiest part, the equations maybe second, and then the table might be less familiar, but we're going to look at that today. So we're going to do that through looking at these three situations. If you've already explored through these on your own, then you're good to go. But this first one just says you receive a spider plant in the mail. The plant is only a ½ inch tall when it arrives and is predicted to grow at least 1 inch per week for the next 12 weeks to reach full growth. Okay, so there's like a situation. Make a table to represent the plant's growth. So we're going to, every time, right, weeks pass by, the plant is going to grow. It's going to grow in inches. So height, I'm going to put in inches. And we just want to make sure that we fill the table with correct data. So week 0, I guess, when you first get the plant, it's a ½ inch tall. By week 1, it grows 1 inch. So now it's at 1.5. Week 2, it's at 2.5. Week 3, 3.5. And you can see where this is growing. It's just growing by 1 inch each week. So we could put as many data values fit on here. And then essentially, we can kind of look at a pattern of growth with our linear. Now, in the past, you probably did something like this, but essentially what we do is we look to see what's happening between each of our output values. And we made the table, so we know that it's just adding 1 every week. That's our rate of change or our growth, or it's often called the common difference because it's common between each output. So this would have a common difference of 1. Now we know that it's linear when there's a common difference adding or subtracting there. So this would be a linear function. And if I want to create a linear function, remember that we create them using like the y equals mx plus b, where this right here is that common difference. This is the slope or the rate of change. And then this is your y-intercept, right? Or your starting value when x is 0. So if I'm creating an equation for this, number 2 asks us to write an inequality, then I need to put in my slope, which was 1, and then I have x, and then the y-intercept, if you look right there before any growth has happened, was 1/2. And we're putting it as an inequality because when we were given the initial information, it said it grows at least 1 inch per week. So this could be greater than or equal to that specific value. So I'm going to put this over here on number 2. Again, for linear, we just need that rate of change and then the y-intercept or that initial value. And we know that the equation is linear, right, when there's only a degree of 1. So there's 1x there, has a degree of 1. That guy would be linear. On a graph, if we were to put this here, we would do something like putting weeks across the bottom. 0, right? Let's go by 1s, but I'm going to label just every 2. And going up the side, maybe we could do the same thing. So when I plot these points on my graph just from the table, I would be at 0, 1/2 when it arrives, and then it goes up by 1 inch every week. And this would cover those 12 weeks. Now again, because it's an inequality, I guess I could shade this above the line. But essentially we're showing that pattern of, right, at least that much growth, and that would be linear. Linear graphs are the easiest to tell. They're just a straight line. So we know on question 4 that this one's going to represent linear growth. Okay, so all of these things denote linear growth. A common difference, adding, subtracting the value, that form mx plus b, so that degree of 1, and then a straight line makes a linear function. The next one you guys studied was exponential last year. After looking in the mirror and feeling flabby, Scott decides he really needs to get in shape. He joins a gym, adds a much-needed cardio workout to his routine. His personal trainer advises him to start slow and work his way up. So he begins his workout for week 1, so I'm going to put that in here while we go. He says week 1. He's going to run 1 mile a day, so I guess this is going to be like miles, and I'm going to do per day. So the first week, He's just going to run 1 mile per day. Every week, Scott will double the number of miles he runs in his workout until he reaches his goal to run a half marathon. So it looks like in week 2, he's going to double the mileage. So he's going to run 2 miles a day. Week 3, he's going to double. So now he'll be up to 4 miles a day. And week 4, it looks like he'll be at 8 miles. And he's probably about ready for his half marathon at that point. We could put this one in. That would be a rough week there, 16 miles a day. So you'll notice on this one, if we were to look at the table, or what we call this common difference, this one's actually called a common ratio, because if you look at this, instead of adding a value, this one is multiplying by 2. So we know that it's exponential whenever it's multiplying, or repeated multiplication there. Okay, that would make an exponential function. And the way we write that, if this is y is equal to, if it's multiplying by 2, right, these are moving up by powers of 2. And we're going to put the variable up in the exponent, and we get x minus 1. Now remember that this right here, when the variable is up in the exponent, that makes it exponential. So linear, again, has a degree of 1. It's mx plus b. Exponential has the variable up inside the exponent. Okay, and remember when you graph these, so let's draw a rough sketch of this graph. So here's our weeks. And I'm going to spread this one out a little bit. So I'm going to put like 1 here, 2, 3, 4. And then maybe I'll just go by ones here. 3, 4, 5, 6, 7, 8, 9, 10. I'll put 5 there. Good. So this is miles per day. And I foolishly forgot to write inches up here. All right, so if we plot these, 1, he was running 1 mile. Week 2, he was running 2. 3, you'll notice we jump up to 4. Week 4, we're jumping all the way up to 8. And then again, if we were to run week 5, he's going to be up at 16. So remember, exponential are the ones that they increase and increase and increase, or decrease and decrease and decrease. But then they come back here, right, and they just get smaller and smaller and smaller and smaller, and they almost flatten out there. That would be an exponential graph. So linear, straight line. Exponential is always increasing, always decreasing, but it's curved there. And again, common ratio there, multiplying by 2. The last one, so the one we've worked on this year, is a quadratic function. So kind of the last part of the one we're going to look at here, it's going to be, again, we have this logos and they're increasing in size, and the only difference between them, it looks like, is the number of blocks. So I'm going to compare the size to the number of blocks here in each size. So we've got size 1, 2, 3, 4. Let's see if we can find a pattern and maybe figure out how many would be in size 5. Now, if we look at this and we come up with the number of blocks, that means we're just up here counting. So we've got 1, 2, 3, 4, 5 blocks in size 1. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 blocks here. So we're just counting each of them. We've got a 3, 6, 9, 12, 15, 16, 17, right? And 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, so 24, 25, 26. So on this one, the pattern doesn't look quite as simple, but again, let's look at that difference between the values. So it looks like in this one is adding 5, then we're adding 7, then we're adding 9. So 5, 7, 9, you could almost guess that the next one's going to add 11 if it's increasing by those odd number values, giving us 37. And this is exactly what it's doing. So notice this one goes out to almost a second difference to find that common difference. This right here, if it goes out to the second difference and it's consistent, that makes it quadratic. Okay, so it would have a degree of 2, right? This one is quadratic. So looking at that, we are just identifying the different parts of our function there, and we can tell that this one is definitely increasing at a different kind of behavior. So this one right here is going to be quadratic. Now, I'm going to skip over 2 and the graph. I'm just going to look at the note parts on this one. To find that formula, again, we could just use the calculator method that we practiced. And we're just going to leave it at that at this point. If you jump down here in your notes, it's just going to go through kind of some more notes highlighting the different parts. So remember linear functions, again, you take this value right here and you can tell that that common difference is adding a value. Okay, so we know that it's linear, and if we want to create that equation, we just write y is equal to whatever that common difference is, that's our slope, and then we look for our y-intercept to fill in the b value, so that would be +1. Our exponential functions, again down here, they're graphs, right? They always increase all the time, or it's decreasing, so it's flipped around, reflected. They always have a variable in the exponent, so this is really hard to see, but that's a variable in the exponent, making it exponential. And then they're always multiplying by a specific common ratio, so whether it's multiplying by 1/2, multiplying by 2, multiplying by 7, whatever that is. And then the last one, quadratic. Again, notice on the table they're going out to the second difference. We've dealt a lot with quadratic graphs. They always make a parabola, so we know they're quadratic. They always have a degree of 2, so if you look at that function, the highest power there is 2. You can also write quadratic equations, right, in like the factored form, or if you see it written in vertex form, that's also a quadratic function. So we can have them in different forms, but again, all of those have those 2 x's that make it quadratic. So you can try it on a few of these as you're moving down. I'm going to go through these ones rather quickly, and then you can just finish out that last page. So looking at this one, it says find a common difference below and state whether the pattern in each table is linear, quadratic, or none of these. I don't really want to deal with the none of these right now, so I'm just going to cross this one out. It doesn't have a consistent behavior. So I look at the x's, they're increasing by 1. I just make sure they're not wonky. And then again, I look at the behavior of the y values. So this looks like it's increasing by 2 every single time. So this one again would be linear. And if I was creating that equation, I would write y is equal to 2x. There is no like 0 in the x, so I'd almost have to go backwards 1. If I subtract 2, that would be 0, so I don't really need to write +0. Again, moving to the one on the right, if I'm looking at the behavior here, this looks like it's going down 5, and then down 3, and then down 1, and then up 1, and then up 3. So this one's definitely parabolic. It's moving back up. You can almost tell the vertex would be right there where it goes down, and then it comes back up. And again, that one's going out to that second difference. It's just adding 2 in that second difference. So this one right here would be quadratic, and we could plug it into our calculator and create that function. Looking at the equations, again, if you look at part A, this one again is in that factored form. It has the 2 x values. This is definitely quadratic. B right here has a variable in the exponent, making it exponential. C just has the 1 x value. This one is linear. D has x squared, making it quadratic. N, notice this one's in factored form, but it has those 2 x's that would create an x squared, so also quadratic. And then this last one has an x in the denominator. This is none of these. We're not going to deal with that one. So looking down at the bottom, again, if it's a straight line, we can tell that this one would be linear. So just make sure we can tell a linear graph. That middle one's a parabola, so we're going to call that quadratic. Down here on the left, also quadratic, anytime we see a parabola. That middle one has too many curves. That one's cubic, so we're going to skip that one. We're going to skip our circle, and then this last one is exponential. Okay, so just distinguishing between the 3 of them if I was given a table or equation or a graph. On the very last page, again, you're going to work through these. I'm going to have you guys skip this one. This one's kind of a ski-wompy example. But the rest of these, just practicing what we just talked about. When you get down to this kind of application problems, it will give you the function. So it gives you that this one is y equals x plus 40. So just put in your x values and see what comes out and fill in that table. And this one is 2 to the x. Okay. Again, you're going to see questions like this on your test, so just be able to kind of distinguish between the three functions.